In this section, we will introduce a very interesting subject of mathematics called topology. Now, topology is probably unlike any math that you've seen previously in your education. Topology is the study of figures that could be stretched, bent, or otherwise distorted so long as you don't tear or separate the figure. So basically in topology, we imagine everything's made of super stretchy or super compressible material, and our only rule is that we can never cut or glue. If we were in class together, we might have some Play-Doh and create shapes and then see how we can stretch or compress that. And there is a limitation there because Play-Doh will eventually fall apart, which would break our rule of not cutting or gluing. But you can imagine, what could I do to deform one shape into another if I had a perfectly stretchable or compressible material? Now within topology, mathematicians start talking about when is something topologically equivalent. That means when can I turn one object into another just by compressing, stretching, bending, or distorting the object as long as I didn't cut or glue. And that's the exact idea of topologically equivalent. Two spaces or objects are said to be topologically equivalent if one can be deformed into the other without cutting or gluing. And here we assume that the material is extremely stretchy or extremely compressible. Because this distortion is allowed, unlike our regular life, topology asks questions about the basic structure of objects rather than the size or the arrangement of the object. And the reason for that is, if I had one box, and if I was normally thinking, is it the same as this box? In our real-world understanding, we'd say no, because one of the boxes is much larger than the other. But in terms of topology, I know I could stretch the material because I have infinite or very stretching and compressible material until I have one exact copy of the other. So in topology, we're focused on features of the object that do not change even if the figure is distorted in allowable ways. And our main focus in terms of that is what will never change no matter how much I stretch or compress an object is the number of holes in an object. And that leads us to the idea of the genus. So the number of holes is the genus of the object. So one of the takeaways so far is if you're asked if two things are topologically equivalent, that's essentially asking the question, do the objects have the same number of holes? Because however many holes they have will stay no matter how we distort the object. Let's practice this with a few examples. Now in this table I have genus 0, which would be the first column, genus 1, which is the second column, genus 2, which is the third column, and in each of these we know genus is the number of holes. And the way this game will work is we're trying to see, of the objects that you see lined up below the table, which are topologically equivalent. And the answer to topological equivalence will be which have the exact same number of holes. Okay. Now let's look at a few of the ones that are maybe a bit easier to see. In this infinity symbol, does it make sense I have one hole and two holes? And in the idea of topology, a hole is something that you can pass through one end and come out the other. So if you've ever threaded a needle, the top of the needle is a hole because you can put the thread through the hole. This is different than what we might have thought as like wells. Wells we think of in our natural world as it is a hole, but there's a bottom to it. It's not that it goes forever and ever and there's a beginning and something that you can come out from the outside. So for us, this infinity symbol has two holes, so it's genus 2. There's two more objects in this list that is genus 2. Can you spot the other two objects that have two holes? That is things that you could come from one direction, completely pass through, and come out the other side. The next is the 8. It has two holes. And then finally, we have the shape B, also has two clear holes. All of these are topologically equivalent. And that means through bending, stretching, distorting, or compressing, I could turn one into the other. Now let's look at the genus 1. Which of the objects have only one hole? Okay, I think two clear ones are the donut clearly has one hole. We can pass through the middle. And the CD also has a hole. Now the last one might be a little hard to focus on. We actually have one hole here in the handle of the coffee cup. You could imagine that I could string a thread straight through the handle, right? Now the cup itself is not a hole because this is just a depression. And this depression, if I'm allowed to shrink or stretch or distort, I could actually flatten the whole cup to where the depression disappears. But this hole from the handle will still remain no matter how I stretch, shrink, or compress. And in this idea of what happens to a coffee cup when it gets distorted, a video that I've linked in our class's Canvas page shows you how you can distort a coffee cup and turn it into a donut topologically. So as all of these are genus 1, we know they are all topologically equivalent, even though they do look like different figures. So a donut is topologically equivalent to a CD. That one's probably pretty clear to see. You can just see that you compress it to where the hole gets smaller and the CD gets larger on the outside. But interestingly enough, the coffee cup is actually topologically equivalent to the donut as well. Look for a video coming up soon about how you can distort a coffee cup into a donut. And then our final figures have no holes, that's why they're genus 0. A banana has no hole. A solid ball has no hole. And this fish also has no hole. Now some of y'all might be thinking, well, the fish has a mouth, right? And actually, I was just thinking about this. Let's not get too much into the biology or the anatomy of a fish. Let's pretend this is a stuffed fish. So it's like a stuffed animal. And in the stuffed animal, there are no holes to the fish, and that's why it's also genus 0. So this was our first practice of determining when things were topologically equivalent. Remember, that comes down to counting the number of holes in the object. If they have the same number, they can be distorted topologically one to the other. Let's practice this with a few more examples. We're asked to determine whether these objects are topologically equivalent. The first is a rubber band. We could imagine that like this. A rubber ball and a rubber band. So a rubber ball is like a child's ball. And a rubber band, something like these. This has one hole, so this is genus 1. Genus is the word in topology to say how many holes. We know a ball has no holes. A solid ball, genus 0. So these are not topologically equivalent. Okay, next we have a football and a cereal box. So here let's think of kind of like a Nerf football where there's no holes for the laces. So we have a Nerf football, solid, and a cereal box. Now our cereal box, although it has an indentation so we can get inside the cereal box, unless we deconstruct it and break it apart, it has no holes itself. So again, it has an indentation, but an indentation is different than a hole. So both of these have 0 holes. And as they're both genus 0, we know that they are topologically equivalent. Now the next one says a donut and an unzipped coat. So imagine an unzipped coat. In an unzipped coat, we have the arm, the body, and the other arm. And for a donut, we know a donut clearly is genus 1. Let's take a moment to think about what is the genus of this unzipped coat. So to have a whole topology, we have to have a distinct beginning and exit. So I think we clearly see there's a distinct beginning and exit from the top of the coat down to the bottom. But there's also a distinct beginning and exit from one arm of the coat out to the other arm. So here, this is genus 2. And as they have different numbers of holes or different genuses, we know that they're not topologically equivalent. Now, there's a few more ideas that we'd like to cover in this section, but they're very hard to visualize or just talk about as we would other aspects of math. Now, lucky for us, there have been people who've made excellent visualizations of these ideas, so I'm going to link that in this week's material. So look through our courses material for this week, and you will see additional videos that discuss things like the Mobius strip, fractals, and how we can turn a donut into a coffee cup topologically. So this is it for what we're covering in this portion of the lecture. This portion of the lecture is focused on identifying when things are topologically equivalent by counting the number of holes in each object. And then for the remainder of material from this section, you'll watch the videos I've posted that go over how does a donut get topologically deformed into a coffee cup, what is a Mobius strip, and what are fractals. So watch these additional videos, and that's all you have to do for this section of notes. As always, if you have questions, please reach out and I'll be very happy to help you.